and radius is RA, and the lower gears, this radius is RB. And here on one side, this is the shaft. RD, yes, thank you. And this is the shaft and linking to ABC. So this is point ABC. So, and this is the lower shaft, and that is DF. I try to take the three-bar diagrams, but once you get familiar with the process, you don't need to get so detailed analysis. Okay. So now for this case, this is TC. Okay, so here by imbalance, this is TC. Okay, and again, this is the welding surface, which means linking this surface to here. Hopefully you can see it clearly from this three-bar diagram. So on the same spot, TC to here, that is the action reaction. Okay, so if TC is going to that way, so let me draw this one. The TC is in this direction, so that means to here, that should be, I'm kind of confusing myself. Whatever, I just draw one direction. How about that? Okay, so this is TC here. Okay. And this one must be balanced by this. So here should be TD. Let me call it T. Let me leave a symbol here. Let me fill up the symbol later. Okay. And this symbol will be related to here. Again, the two gears must log in and imbalance. So the two will be in certain relation. And now what is this? Basically, this is here. From here we have, this is TF, right? Probably too low. Let me get that one a little bit higher. So this is TF. This one.
Just really quick, for RA, the TC on RA. So when you're drawing that, because it's flat, but
yeah. So you know what I mean, okay? And we just pick one direction.
Okay.
To drawing here, the TC is here. Then the TC will be driving top in that direction.
Okay. Yeah.
Okay, will that be good?
Yes.
Okay. So, and then from here we continue. So this is the TF. So basically this is an action reaction to here. So clearly this substrate must be TF, right? Okay? So in this way you can see TC and TF can be related to the gears by, if you remember that equations.
Excuse me, Professor.
Yes.
For TF, the direction of TF, wouldn't that be going in conjunction with the TC? So they'd be, because the two gears as they come together, they're going to rotate together, sort of like that. So wouldn't TF be going in the opposite direction if it was in static?
You mean saying like this?
Yes, because then the two gears are opposing one another.
Because you're forced at the point where they touch, they have to be opposite and equal, right?
Yeah, so they should be opposite.
Well, they're
together.
coming together and rotating.
Oh,
like
yes,
that, so.
right. Should be in this way.
Yeah.
Good. Okay. So basically, much better than I do. Okay. Anyhow, and from here the TC. If you remember, if we draw the gears individually, so this is RA. The questions in discussion is we get the two gears in balance, they're locking. So basically the two torque must be opposite, which must be, the two gears must feel rebalance from the other. Okay, using that feeling to set up the right direction. But right now it seems I have a hard time to view what I'm drawing, so but anyhow, that is this. Okay, now to get this one, and again, here I try to dig into the detail to write up the formulas. But once you get familiar with, you don't have to do this. So this is RA, and here this is the RD, and this is the contact point. So this is TC, and this is the contact force. Contact force at the contact point is action and reaction, so the same magnitude but opposite directions. Okay, so for this case, TC equal to RA times F. And here, for this case, this is TD. So TD equal to RD times F. So using the two relations, we can get is F on one side, on the top is equal to TC divided by RA. And here, to the bottom equations, F is also equal to TD divided by RD. Sorry, I kind of changing TF, right? So that is TF. So therefore, here we find out that TC equal to TF, RD, and RA. So using these relations, so here if, let me write it down, that relation here. Will that be okay? And again, this is one of the properties on the gears. So let me write up that equation, that relation to here. So here the TC equal to RA, RD times TF, and RA equal to 4, and RD equal to 2.5 TF. So that is, we'll keep that one here. So now those are the two relations we have to use. So with the two relations, then we check individually the shaft. So in shaft BC, the upper shaft, for the shaft BC, we check the design criteria, the maximum less than or equal to 7,000. So that means here the TC over J for shaft BC is less than or equal to 7,000 and pounds per inch square. So therefore, the T in BC, in shaft BC, must be less than or equal to 7,000 multiplied J over C for BC. Okay, and actually what is this? This is the torque in shaft BC per our notation, that is TC, right?
Excuse me, Professor.
Yes.
So if we're trying to solve for the largest torque in TC, why would we solve that initially? Because if we
Yes.
substitute it in,
Yes.
wouldn't it disappear?
Yes, and
So
give me
we're solving
time.
for-
Give me time to go over the whole process. And his question is this: this is design, and why not we pick up the other route and for quicker, maybe the quicker go to the solutions. There's a couple possibilities, and let me finish this one. Give me a few minutes, and you will see. So this is TC, and we plug in here, and that is 7,000 multiplied with C equal to the radius of the BC. This is the diameter, so the radius is 0.08, and J is pi over 2 times 0.08 to the fourth power. So we plug in those numbers carefully. The T should be equal to 5,630 pounds per inch. If the TC in shaft here is less than that one, then we can use this equation. So therefore, the TF, using this relation, TF equal to 2.5 divided by 4 times TC. So this will be less than or equal to 3518.8 pounds per inch. So right now we have two numbers. The two numbers are checked against the first criteria. So this means with the two numbers, we will guarantee the maximum stress in shaft BC will meet the criteria. But we don't know that will be satisfied by the lower shaft. So we check another shaft again. And lower shaft is, let me call the EF. Okay, so this is not determined yet. This is not the final answer yet. Because this will satisfy the shaft BC only, right? Because this is a criteria, and this is well for shaft BC, but not for shaft, the other shaft. So for this one, and again, the TC over J, for this shaft, EF is less than or equal to 7,000 pounds per inch square. So therefore, from here, we can see T for shaft EF is less than or equal to 7,000 multiplied with J divided by C for shaft EF. I simply move these coefficients to the other side. And here, so that would be equal to, so therefore here, this is the shaft in EF, and that actually per our symbol is TF, right? TF is less than or equal to 7,000 multiply J for the shaft EF. We use this information here. The radius is 0.625 and pi over 2, 0.625 to the fourth. And this one is 2684 pounds per inch. And then, therefore, using our relation TC equal to 4 divided by 2.5 TF. This one will be less than or equal to, this number would be 4300 pounds per inch. To make the shaft EF satisfy with these design criteria, we have the numbers here. So, was that clear to answer your questions? Yes or no? Not yet.
I
And
don't understand.
let me
that
explain.
knowledge
Let me
exactly.
explain. This is the first criteria, and this is the second criteria. For the questions we're asking is the maximum stress in both shafts must be less than or equal to this number. So that means the torque we apply must have the two things be satisfied, right? Okay. Now for meeting the first criteria, we have this range. For meeting the second criterion, we have this range. So here you can see for the first range, we have the first option, TC less than this number. The second option, TC less than this number. So which one? If we choose the TC is 4,300, then this will make this range satisfied, which means this will satisfy. Are we okay? Anyone have any other questions? So in this case, we have to choose to make the both criteria satisfy. So that means the TC must be less than this number. And TF, again, that is must go to these directions. And again, the TC, TF satisfied from the same group, so they will meet this criteria as well. They will be in balance. Are we okay? So which means if I would change, for example, if the problem would be changed to, say, the maximum stress here is 7,000 psi, the maximum stress here will be 8,000 psi. So probably you can repeat the same process, similar process to determine the range. And your question, I believe, could be starting point, could be starting from here. And then, but here we have to check another part. Okay. Think about this and the next one. This one again is another design problem. The gear set is arranged like this. So we twist one shaft and the torque will be transmitted to this gear. And that torque will be through the gear relation to transmit to the larger one. And that will produce the corresponding torque in this shaft and actually it will be line. So for this case, we have two design criteria. The first one is we have to make sure the maximum stress in both shafts must be less than this number, 60 MPa. The second criteria is this. The angle of the twist, the angle of rotation at D must be less than or equal to 1.5 degrees. So under the two criteria, we want to determine the radius, the diameter of the shafts, and assuming they are the same diameters, the both shafts have the same diameters. So we want to determine the size of the shaft and to make the things happen. And before we do it, we must know that the shaft must not be too thin. If the shaft will be too thin, then the angle of the twist will be too large. So that means here basically you should looking for some value is greater than or equal to some threshold. Okay, so that's the first case, the first step before we move. So now again we try to dig into the information carefully for those. So save this, and we can write down the all the needed information here. So the first one is the angle of the twist is V equal to TL over GJ. And also for the information, the V at D, if we take the relative rotations, the relative rotation basically is D relative to C plus VC. Okay, and the third information we would need is this. In a similar way, this is the gear C, this is RC, this is the gear D, gear B, RB. Okay, so this is the shaft linking to the gear C. So that means the cup here, the cup of the marker represent is the empty. So we apply the torque to here. So basically the torque we apply the torque in this way, so that will transmit it to the gears in this direction. Let me call it TC. Okay, and then this one in balance, that will be go that direction. So this will be TB transmitted to the gears. Okay. So the TC and related to TB, the same thing we just done here before. So that means TC respect to RC equal to TB respect to RB. Okay, so for this case, we have is this TC will be equal to RC, RB times TB, and that will be equal to RC equal to 40 millimeter, RB equal to 100. So with those informations ready, we can begin to look at the problems. So right now we are given is the T is here. So for the shaft, this is a D, this is a C, and here we apply the torque and in this orientation. So this is the 1000. The unit is Newton meter. So in balance, we must have this, and that is 1000. So basically this value in TCD is 1000 Newton meter. Okay. So therefore transmitted using these equations in TAB. So TAB here being transmitted using this equation here, so that will be equal to T, will be equal to using these informations, and the torque transmitted onto the TB, so that is TAB, equal to 100 divided by 40 times TCD. Are we okay? We're using this equation.
Isn't D pointing out the torque the other direction?
Oh yes.
The other
Okay.
one too?
And this one will be the same.
For CD as well?
For D, oh yes.